Okay, so now we have our cost function formulated, and we can start differentiating this one, set n equal to 0. So how do we find the minimum? We, of course, because it's smooth, so we can differentiate the set that 1 equal to 0, solve it, find the critical value, and then we're all set. So let's do that. So we have a d, cy, dy. Of course, the derivative is with respect to y. So set this one equal to 0. Now you start differentiating this guy. When you're differentiating the first term, you get just a constant c of, right? Now when you differentiate the second term, you get a what? You get actually two terms. This is what your Leibniz rule comes about, right? So there is one term, like you replace the whatever the variable here, the damping argument by the variable y here. There is also a differentiation inside here. The damping argument y here, because in the lower integral you should have a negative quantity comes out as chain rule of differentiation. Everyone remembers that, right? I mean,
what did you just say?
let me put it here, okay? So if I have a g of x.
I know what chain rule is.
Yeah, but I mean here is a function of, say, f of y. I'm using different. You like y instead of x. Suppose I want to differentiate this one. Then what happened? Well, let's do it even simpler. So here is y. Here is f of
maybe a less general case.
Let's do this one first.
Okay.
The derivative of that with respect to y, what do you get? You get, first, you get a term, I'm talking about the p prime of y. You get a term of y substitution, right, from here. And then that term, you have to differentiate with respect to the upper limit, the variable. But the variable, ddy is equal to 1, so nothing. But if you have a by, then you have a dby, dy term comes out, terms of differentiation. That's one term. But you also have another term, 0 to y, partial with respect to y, f xy here.
Was there some class that you learned that in?
Yeah, in your 202 or 203.
Which is Calc 2 and Calc 3?
Yeah, or advanced calculus at FERC. You know, that's fundamental theorem of calculus, one version of that, sort of.
It must just look different.
Yeah. But this rule we are talking about is called the Leibniz rule. Okay, so if you have that term over there, if instead of y, you have by, so here you have b prime of y, chain rule of differentiation. You have to do that. Okay?
Okay. How about the ay on bottom?
I'm sorry?
How about ay?
Ay, the same, except that you have a negative because it's in the lower limit. So you have a...
So you should have 3 parts for the differentiation
Yes.
function, right?
Yes. Yes. So if you have, here I put in a special case, this is the 0. If I put an ay, then you have the negative quantity of replacing x by ay, right? So,
Are we going to need to know this process
yes,
very
in this
well?
process.
Very well?
Yeah.
Could
I
we
guess
maybe-
you better review it.
Oh, could we maybe do a review of it?
Yeah, right.
But, I don't know.
What, yeah.
Maybe with numbers or colors or like zoom animals or something.
So maybe we'll do that first, see how that goes. If that really needs to go back to the general case, we can do that. Would that be okay? But look for your book on Leibniz rule. with variable limits
In this
on the
book or
integral.
in?
No, in the calculus book.
Okay.
In the calculus book, or you pick up any book from the library and look at the section on calculus. But it's needed.
Leibniz rule
Yeah.
for what?
Uh,
You said something about the limits.
yeah, if you use it for differentiation.
You said something about
Variable,
Leibniz
variable limit.
variable limit.
Yeah.
Hmm.
But if you look at that, even you just look at the index for Leibniz rule, you will see that. Okay, so now let's differentiate this guy. So here we get actually two terms. One term is do the substitution like we did over there, but this one is y minus y, so that term actually equal to 0. So you don't have that, but potentially it's there. And then you should have a negative, but in this case it doesn't matter because y minus y is equal to 0. However, you have another term, that's p, the integral from y to infinity, x minus y. Now here, you want to take the partial with respect to y inside, and then phi of x dx. Okay, so the first term is zeroed out because I do substitution, y minus y equal to 0. Now here, the next term I get h, and I do the same thing. If I do the substitution, I get what? I get, say, y minus y times phi of y. Maybe I'll write that term as well. So just, it's p y minus y phi y, but with negative sign because it's in the lower limit. And then plus p, the integral from y to infinity, partial with respect to y, x minus y, phi of x dx, right? Now here I do the same thing for the next term. So I get h times y minus y. This time is positive because it's the upper limit. And you get a phi y, but that's also equal to 0. Yeah. All right, so here you get h, the integral from 0 to y, partial with respect to y, of y minus x, phi of x dx. So when you are taking the partial, you are holding x as a constant. So the first term will disappear. The second one give you a negative 1, right? So now let's continue. So from here, you get p, but you get a negative 1, as we said. The integral from y to infinity phi of x dx. It's a partial. Now the next one, when we take the partial, is a positive 1 because it's y minus x. So we get a h, the integral from 0 to y. Here you have phi of x dx. Right? Any doubt?
Oh, no, negative 1, never mind.
Yeah, the negative
I was
one
wondering
is,
why it was minus p.
yeah,
but
yeah, because it's the lower limit.
Right.
The lower limit, as you can see, I said if you put it here, right here, then you have a negative. How do you, by the way, how do you prove that? How do you prove this derivative of that is equal to the stacked weight? Well, it's a good homework problem. Maybe you should try that. Let's pose that as a homework problem. Variation of that. I'll write down that later. Let's continue. When I finish the problem, I will write down that problem. Ask you to look at. Okay, so when you look at this term, you see that really is something familiar. So is this one. What? Because
Density function?
it's the distribution function.
Distribution.
It's by, again, fundamental theorem of calculus, this is from 0 to y. So really, you could have from negative infinity to that, but we assume, everything we order is actually positive. So here the function has to be having some positive value. So that now if this is the distribution function, what is this? This is the complement of the distribution function, or 1 minus f of x, right? So I can put this one as 0 equal to c minus p times 1 minus f of x plus h f of x. See, what is our objective? Sorry, not x, but y, because the variable is y, right? This is the y, this is the y. So, what is our objective? We want to find the optimal value of y. But can we find that from this equation? Yes, in a way we can. It's not the explicit solution, but it's a solution of an equation. So you see, I can simplify that. It becomes 0, c minus p plus p times f1 plus h times f1. Right? If I move things around, I can collect the common factor p plus h and move this to the other side. And the shortage minus the c divided by p plus h. That's your solution. You would say this doesn't look like a solution, but this is the distribution function. If you give me a value of this, I can figure out inversely what the y is corresponding to that. For example, very often what we are dealing with is exponential distribution because we don't want the outer quantity to be negative. We could put something like, as I mentioned, from negative infinity, but the point is that for the outer quantity, it's not going to be negative. So that's why we normally use something like exponential distribution, uniform distribution, or things like that. Even uniform distribution is not like in a symmetric interval from minus something to positive something, but in a positive territory, right, from that part. So this one is the solution. So for the one stage stochastic inventory model, if I ask you what is the solution, how do you choose the one? You choose the one so that this condition is satisfied. If you think about it, what we did last time by finding the reorder point and the reorder quantity, we essentially did the same kind of thing. You are given some distribution function, you are trying to figure out what is the inverse, what is the corresponding value of y, or a critical value for that. So this is the solution for that problem. So I'm going to continue on that perhaps next time because of your suggestion. So I think I'll spend a few minutes on the differentiation part because you need to do this for all the problems in this part. So let me start with a simple one, and then you can add on that. So I'm going to look at the problem as I mentioned over there. It's g of y equal to the integral from 0 to 1. And I'm going to look at even no, well, let's put x there as 1. So I want to find the derivative of this guy. So how do you find the derivative of that? Here's the definition. This is the one-dimensional thing.
The limit definition?
Yeah,
The
here's the
difference
limit
quotient?
definition. Yes, yes. So what do you do? you look at G, you perturb that, you simply perturb that slightly by delta y. So I'm going to simply write down as delta. Forget about the y. And then you are going to subtract G of y from there. And then you are going to divide that by delta, take the limit as delta goes to 0, right? So now first let's look at what is this guy. That would be equal to the integral from 0 to y plus delta. And here, every time you see a y, you should replace that by y plus delta. So here, I have that, I have y plus delta. By the way, my function is smooth enough, right? Not only continuous, but differentiable. So I didn't write down other conditions, but I think it's clear, right? So this corresponding to that guy, right? So then I'm going to write the integral from 0 to y f of xy dx. That's this guy. Okay? Right? So now you see there are two places this appeared. It appeared here, also appeared here. My hope is that I can compare those. I can look at the difference of this. So here it looks like I cannot quite do that yet. So what I do, I add something, I subtract something. So I would add minus f of x comma y, and then also plus that term. Okay, so let me just do that. So I do the simple one. I'll ask you to verify the more complicated one yourself. All right. So now, by concentrating on the first term, I have the 0 y plus delta. Say f of x y plus delta dx. Now I'm going to subtract f itself. Let's write it this way. But if I subtract this term, I better also add that term back, right? So I have the other one from 0 to y plus delta, f of xy, dx, minus the integral from 0 to y, f of xy dx. So that's g of y plus delta minus g of y equal to this quantity. Now I'm going to divide by delta, both left-hand side and the right-hand side. Here, when you divide that by delta, you simply put it here. Here, when you divide by delta, you have 1 over delta right here. Now, can you evaluate this one? When you evaluate that one, what happened? You'll get a partial of x with respect to y, right? If I take the limit as the delta goes to 0, right? I mean, here, if you look at this. Now, if you are doing the difference quotient, you are holding x as a constant. So the only thing vary here is y. So it's y plus delta minus y for the second variable. So here, if you are looking at this, you are looking at some sort of difference quotient. The difference quotient as a limit gives you nothing but the partial of f with respect to y. Clear? So this one goes to, now you would say, there is a still term like this. But when delta goes to 0, y plus delta goes to what? Goes to y. And by continuity of a linear function. So that part, the integral becomes from 0 to y. Right? So that this term is settled, basically using the partial derivative argument. I didn't write down the detail, but you see you can write down, right? So now if I change that to some function of a, you see the chain rule of differentiation would appear by the same idea as what we did, but you need to do more work. Now, what about for this term? What can you say for this term? This term you can switch around, all right? So instead of minus, you make it plus. If you switch the order, the limit of upper and the lower limit, you change the sign of the integration, right? So it becomes plus. But when you make it plus, then those two guys is like the integral from a to c plus the integral from c to d. What is the resulting integral? It's from a to d, right? So therefore you have the integral from y to y plus delta f of x1 dx. And here is divided by this guy. Now, what you want to demonstrate is that this coming out the limit, if you take the limit, as delta goes to 0, what should you get? You should get the function in the integrand, f of x comma y. Why is that? Anyone remembers anything from calculus here? Check on your book. There is something called the integration intermediate value theorem or mean value theorem for integral version of mean value theorem. So they're basically saying, if you integrate this, what you get is some value in between y and y plus delta. So you'll get f of x, some value c. C is between y and y plus delta. And then the integral will be integral from y to y plus delta dx. But this integrand is 1, so when you integrate that, you get y plus delta minus y. And don't forget, you also have another delta. So this cancel each other. This guy goes to y. So you have f of x, y in there. So that's what that is. I didn't do the full proof, but I hope the motivation is clear how you should write that. If you really want to write that in a correct way, you have to use sort of epsilon and the delta or limit result. But here, if we are using the integral mean value theorem, it should be equal to a value, the c here, c is in y plus delta. So when delta shrinks, this one becomes 1 point. Now this, by continuing